In the previous lecture, we began talking about Chapter 3, talking about chemical reactions and then chemical equations. And one of the first laws we talked about relative to chemical change, which also is true for physical change, is the law of conservation of mass. Basically, we simply said that in a chemical reaction, we neither create nor do we destroy mass. We may change it physically, different physical states. We may change how it is combined, but the actual amount of mass we start with is still the same as the amount of mass we end up with. We also went on and said that because then atoms have a very specific mass, if mass is conserved, then quite logically atoms themselves must be conserved in a chemical change. And so looking at then that aspect, we said that we can use a technique then to write a chemical equation and then to balance that chemical equation. In other words, the number of atoms that we have appearing on the reactant side, the starting side, should be equal to the number of atoms of each of the kinds of elements that appear on the product side. And that we called balancing the chemical equation. We began by looking at one example the other day, so we will take up there this morning and look at a couple more examples of balancing chemical equations. These are, again, from Chapter 3 that we're looking at, and I'm looking at some of the questions at the end of the chapter. Problem number 2. And I believe in our previous lecture we had looked at the balancing of 2 Part C. I'm going to go ahead and back up then this morning and take a look actually at 2 Part A for balancing a chemical equation. This is what it looks like to start with. And of course, part of balancing a chemical equation is, first of all, we must write correct chemical formulas or correct chemical symbols for each of the reactants involved and each of the products formed. Now at this point we don't have the technique, we haven't studied the technique of how we name and write chemical formulas, so we don't need to worry about that aspect, except for the fact that once we are given the correct chemical formula, as will be the case, we cannot adjust any subscript number, because if we adjust the subscript number, we're actually changing the chemical, not balancing the atoms. So once we have written down then the correct chemical symbols and formulas, then we can't change anything except for the number preceding each of them, which we refer to as coefficients. All right, starting in this particular problem then, again, we look to balance the elements other than hydrogen and oxygen first. And usually we start with the elements furthest to the left and balance them, work our way across, and then finish with hydrogen and then finally oxygen in our balancing if they are present. So in this case, we probably would look at this equation here, and we might start then by saying, all right, let's look at the sodium. Looking at our periodic table, sodium is furthest to the left, and so we'll balance the sodiums. And so we'd say, all right, we have 3 sodium atoms on this side, and we have only 1 sodium atom on this side. So we need to balance the sodiums, and to do so, we will then go ahead and place a 3 in front of the NaCl. Remember I said you can't change the subscript, you need to put a coefficient instead. Now at that point we have 3 sodiums and 3 sodiums, so that's all right. We now look over here at the irons, and the irons, we see that we have just 1 iron here and we have 3 here, and so we could go ahead and put a 3 in front of the iron. So right now we have balanced at least initially then, the iron and the sodiums. Now, in this particular case, notice that we have a group here, and I'm going to put a parenthesis around it. Notice that the PO4 as a group hasn't changed from the reactant side to the product side. When we have groups, which we refer to as ions in many cases, or polyatomic ions, if we have groups in a chemical equation, we can balance it as a group rather than as individual atoms, because as long as the group stays together, we have the same number of atoms of each present. So, what I'm going to look at here is I'm going to say I have one of these phosphate, one of these PO4 groups on the reactant side. I have two on the product side. And so I need to balance then the phosphate as a group. To do that, now I can't put a subscript in because that would change the compound again. I will need to put a 2 in front of the sodium. Now, keep in mind we had previously balanced the sodium. And now I've changed the number in front of it, and if we do that, and we have to do a good job of bookkeeping as we go along, we have now unbalanced the sodium by balancing the phosphorus and the oxygens in that PO4 group. Well, that's all right, that's no problem. Now we'll just go back and rebalance the sodium. Now we have 2 times 3 would be 6 sodiums over here. We need 6 sodiums over here. So let's just, for our purpose here, we'll mark this out and we'll put plus 6 NaCl's. Now we have 6 sodiums on both sides. So let's just do a quick check and see where we are at this point in the balancing. We have 3 irons and we have 3 irons. We have 3 times 2, we have 6 chlorines. We have 6 times 1, we have 6 chlorines. We have 6 sodiums, 2 times 3, we have 6 sodiums. And we have 2 of these phosphate groups, and we have 2 of the phosphate groups. As a matter of fact, checking now the individual atoms, we have 2 times 1, so we have 2 phosphorus. We have 2 times 1, we have 2 phosphorus. We have 2 times 4, or 8 oxygens, and we have 2 times 4, or 8 oxygens. So even on an individual element basis, every atom in there is now balanced. Thus fitting, as we say, the law of conservation of atoms in a chemical reaction. So as you go along, if you rebalance something that you previously balanced, you have to go back and make a correction. So you can't just think that once you've balanced something, that might be the end of it. You need to continue your book work. All right, let's look at another one here. Or were there any questions on any of that one? All right, let's look at this one here. This is part 2E in the text. All right, in this particular case, we can look at this and we can say, all right, we'll start with the iron. Iron and silver there are pretty close to each other. It really wouldn't make too much difference which we would start with. But seeing iron is first here, we'll go ahead and start with it. We have 1 iron atom on this side and we have 1 on this side. So the irons are balanced. We have 1 silver on this side and we have 1 silver on that side. So it is balanced. But if we look at the NO3, again we can look at it as a group, because we see that it's all as NO3 over here. Or we could look at it as just individual nitrogens. Either way would work. We have 2 nitrogens over here and only 1 over here, so we would have to put a 2 in front of the silver nitrate to get my 2 nitrogens. And when I do that, I have 2 times 3 or 6 oxygens, and I have 2 times 3, 6 oxygens. But we unbalanced one thing. We unbalanced the previously correct silver. And so now we see we have 2 silvers on this side, so we must complete our balance now by placing a 2 in front of the silver on that side. We now have every atom in there properly balanced. Any question on any part of that? If you get yourself going where things really get messed up in terms of that you start messing up several things in the same equation, the best thing to do is probably just go ahead and scrap it and restart and pick something else to start with, and that usually will make it easier to end up balancing. Let's look at this one then as one more example. This is 2 part G. Here we have a compound C2H2. This is called, that's a hydrocarbon. Notice it just has carbon and hydrogen, as we talked about in Chapter 2. It's a hydrocarbon. It's not an alkane hydrocarbon because, remember, the chemical formula for an alkane or a saturated hydrocarbon was CnH2n plus 2. So obviously that doesn't fit that particular formula. So it is not an alkane. All right. Now, as a matter of fact, this is the common name for this is acetylene. Anyone that has worked with an oxyacetylene welding or cutting torch, for instance, here's our oxygen, this is the acetylene, these are the 2 we combine to then produce a flame at high temperature so that we can cut through iron or weld iron together. So it's used as a torch. We start with, in this case, carbon. Anything other than hydrogen and oxygen first, and we look at carbon. We have 2 carbons over here and only 1 over here. So we would start by putting a 2 in front of the CO2. We have 2 hydrogens on this side, and we already have 2 hydrogens on that side, and so that's all right. We then take a look and we count up the oxygens. On this side we have 2 times 2 for 4 plus 1. So we have 5 oxygen atoms on the product side. How could we get 5 oxygen atoms on the reactant side? Well, we could take 2.5 oxygen molecules because there are 2 atoms per molecule. We can take fractional molecules, but as I said in a previous lecture, we can't take fractional atoms. So you could never have a balance where you were dealing with a single atom, but we can have a fraction where we're dealing with a diatomic molecule. Now, the general rule, however, is that we do not want to balance a chemical equation with a fraction in it. And so the question is then, what can I do to the entire equation to get rid of this fraction of 2.5? And I think you probably would say, let's multiply everything through by 2. That'll give us all whole numbers. We will not have changed any of the relationships. This was balanced, so we're going to end up with 2 C2H2s plus 5 O2s yields 4 CO2s plus 2 H2Os. If we do a quick double check here then on the balancing, we notice that we have 4 carbons, and over here we have 4 carbons. We have 2 times 2, we have 4 hydrogens. We have 2 times 2 or 4 hydrogens. We have 10 oxygens on this side. We have 4 times 2 would be 8, and 2 times 1 would be plus 2. 8 plus 2 would be 10, and so all of the atoms are balanced. So if in the balancing we end up with a fraction in it, then we will multiply through by the appropriate number. And in most cases, this is going to be a 2. We're going to multiply through by the correct number to get everything to a whole number. Any question on any part of that one? Okay. Well, I think we probably have spent enough time just on the balancing process. We'll do this as we go along, looking at some problems involving calculations, stoichiometry, which will be a part of this chapter as well. But before we turn to problem solving based on balanced equations, I want to talk just a little bit about some reactions involving the organic compounds that we talked about in the previous chapter, in chapter 2, where we talked about the hydrocarbon compound, the alkanes. There are a group of chemicals, or I should say a group of elements as a family, F2, Cl2, Br2, and I2. The four elements that we see over here stacked on top of each other, element number 9, 17, 35, and 53. These are referred to as a group of elements as the halogens. And if we react the halogens with hydrocarbons, we produce a group of organic compounds that we refer to as halogenated hydrocarbons. Now, the reason that I specifically picked out this group to look at is because halogenated hydrocarbons are some common chemicals that we utilize quite extensively and that have been in the news quite extensively. For many years, we have been concerned with a particular group of halogenated hydrocarbons, which we call freons, and their interaction with the ozone layer surrounding the Earth's surface. So here we're going to first take a look at a couple of examples of halogenated hydrocarbons, and then we'll talk a little bit about how they could possibly be affecting the ozone layer around the Earth's surface and what effect that can have ultimately on us. Well, let's start with a very simple hydrocarbon, the simplest one that we had in the table that we looked at for alkanes, CH4, called methane. And as I mentioned, that commonly is called, or sometimes called marsh gas, and also that's the major constituent of what we refer to as natural gas. All right, if we take methane now and react it with, let's say, bromine, we can form a product and let's see, to have this balanced, I believe we need a 2 right over here. All right, so we're saying that methane molecule can react with 2 bromine molecules and produce this molecule of this compound CH2Br2 and 2 molecules of this compound HBr. Well, this right here is then a halogenated, because it contains a bromine, it contains one of these halogens. It's a halogenated hydrocarbon because we started with a compound containing only carbon and hydrogen. This particular compound would have the name called di, which is the prefix for 2 that we mentioned in chapter 1. Not D, a B, dibromo for bromine, dibromomethane. So notice we still use the basic name of the hydrocarbon from which it was produced, and then tell what things have been attached in place of the hydrogens that were previously on the hydrocarbon. 2 bromines on a methane. And in order to put them on the methane, we have to take 2 hydrogens off. And so there we have the chemical compound dibromomethane. Another halogenated hydrocarbon that you may have heard of before is the one in which we take methane and replace 3 of the hydrogens with chlorines. Has a chemical formula CHCl3. Chemically, we would call it trichloro, because now we're using chlorine, trichloromethane. And trichloromethane has a more common name of chloroform. So if you have ever worked with collecting biological species, etc., you may have used chloroform to either anesthetize or actually to kill them. If you're collecting insects or something like that, you may put them in with a piece of cotton with some chloroform to then kill them to help preserve them. Okay? Or in smaller amounts, of course, chloroform can be used as an anesthetic. This is the one frequently in the old westerns where the bad guy would pour something on a handkerchief and slap over the maiden's face and hike off with her. Okay? That was a chloroform that they were using. It's been around for many years. Halogenated hydrocarbon. One other one, which you may have heard about, this one we take and we replace all of the hydrogens on methane with chlorines. So it has a chemical formula CCl4. We've taken all 4 hydrogens out and replaced them with chlorines. This would be called tetrachloromethane. Again, because we're starting with a hydrocarbon methane to make it, but we're putting in 4 chlorines in place. And this also had a common name of carbon tetrachloride. Now, carbon tetrachloride for many years was used as a cleaning solvent in the dry cleaning industry. As a matter of fact, it wasn't too many years ago that you could go to the grocery store and buy a bottle of carbon tetrachloride, had a little sponge on the top, and if you had a little grease spot on a piece of clothing you wanted to get out, grease is not soluble in water. You could use carbon tetrachloride because most greases and oils are soluble in carbon tetrachloride. And you'd sponge it off and then wipe it out and then wash the clothing and get rid of the grease or oil spot. Well, the problem was that we then discovered that carbon tetrachloride, as many halogenated hydrocarbons, are possibly carcinogens. And because of that, then, of course, we could no longer allow this to be used in a person's home. Also, carbon tetrachloride was quite flammable. And so there was a danger if you were using it on cleaning a garment, had the bottle sitting close to an open flame. I don't know why you would do that, but if you had it setting close to an iron, let's say, and you had a spark, the spark in a short in the iron might be enough to begin an explosion of the carbon tetrachloride. So it has been removed. But the one that we hear the most about is a compound called difluoromethane. Difluoromethane. Notice that we have 2 chlorines and 2 fluorines on this molecule. So chemical formula would look like this: CCl2F2. Difluoromethane. This is the chemical that for most of us we think of as Freon. This is the chemical that was actually produced, manufactured to serve as a refrigerant. It has many wonderful properties. It is not chemically reactive, not toxic to animals or humans. It doesn't react with anything. It has no odor. It has no taste. Previously, before the Freon was produced, then the common refrigerants were sulfur dioxide and ammonia. And both of these have some bad properties. Ammonia, if you've ever smelled Windex or ammonium salts, if you ever happen to have gotten injured and partially unconscious in sports or something, they gave you a little sniff of ammonia salts, you're smelling the ammonia. The ammonia is not very good for us in high quantities. It has a terrible odor, it has a bad taste, and it's very soluble in anything with moisture in it. And ammonia has never become the flavor of the month in ice cream that I know of. So if you get a leak in a refrigerator that has ammonia, you immediately have contaminated all of the dairy products in there. And this was a problem. Of course, this is why the dairy industry was especially looking for something that had no taste, no odor, etc., and was not toxic. Sulfur dioxide is one of our major air pollutants, as a matter of fact, and leads to SO3 in the atmosphere and acid rain, a topic we'll talk about a little later, I believe, in the chapter on acid and base chemistry. But this compound here had all of the good properties that one would want for a refrigerant. Well, it was used as a refrigerant, it was used as a propellant, so that we didn't have to get the shaving cream out or lather it up. We could push a button, it'd come squirting out of the can, or the whipped cream, instead of needing to dig it with a spoon out of a bowl and putting it on. We could just grab a can and spray it all over the place. So it was used for all these purposes as well. But somebody became concerned in studying the effects or a trend in the ozone layer in the Earth. And it was noticed that the ozone layer appeared to be decreasing. And as such, the question was, what is causing the ozone layer to decrease? And many models have been produced. But one of the suspected villains in this process may be Freon. I say maybe because there are so many variables involved in studying the reactions in which Freon may be involved, or other chemicals. We're now suspecting that things like nitrogen dioxide from automobile engine exhaust may be almost as bad a culprit as the freons are, and interacting with ozone. Well, let's take a look at how this halogenated hydrocarbon then can affect the ozone layer. First of all, we have to know what ozone is. Ozone is another form of oxygen. Normal oxygen is diatomic, O2. Ozone is a triatomic molecule, 3 oxygen atoms hooked together to make a molecule. We refer to, when we have elements that can exist in more than one form, we refer to them as allotropes. So that's a word that you want to keep in mind, allotropes. Now, we talked previously in Chapter 2 about isomers, structural isomers of compounds. That's hooking things together differently with the same chemical formula. That's an isomer. An allotrope are 2 different forms of the same substance. In other words, O2 and O3 aren't the same from a chemical formula, but they're both the element oxygen. And so these are referred to as allotropes. So oxygen is an allotropic form of oxygen. Now, ozone, first of all, is produced outside, the furthest part of our atmosphere that is subjected to high energy radiation from the sun. The oxygen out in that area of the atmosphere is subjected to these high energy ultraviolet rays that are coming in from the sun. Actually splits the molecule into 2 oxygen atoms. These 2 oxygen atoms react with 2 normal diatomic oxygen molecules to produce 2 molecules of ozone. Now this process is going on and on and on and on and on continuously in that outer part of the atmosphere. Well, why do we care about ozone? That would be the question. Why do we care if it disappears? Well, the ozone molecule acts as an ultraviolet absorber from the sun. Coming in from the sun, we have all sorts of different wavelengths of energy. We have visible light, which we can see. We have infrared energy, which if you stand out on a sunny day, which we're not going to probably have the opportunity for a short time, a period here at least, to stand out in the sun. If you stand out in the sun and feel warmth from the sunlight, that is due to the infrared. Obviously, you can see the visible part. But there's also some higher energy parts that we don't see called ultraviolet. And it is the ultraviolet that causes, for instance, one's skin to tan. This is a chemical change. Ultraviolet energy breaks some of the chemicals in the skin, reforming them back into then, or stimulating the formation of a chemical which then protects us from other ultraviolet. So we're building up our own immune system when we tan to protect us from ultraviolet energy. Now, ultraviolet energy then that reaches the Earth's surface can cause then organic cells, biochemical cells, to undergo change, to mutate. And if we're subjected, ourselves, plants, animals are subjected to high intensities of this ultraviolet energy, we can get all sorts of mutations occurring. One of the type of mutations in human is skin cancer. Cancer is a mutation of normal cells. Plants could become mutated and change to a form that may not be helpful or may run wild and just grow like mad in the mutated form, just like a cancer does. So we need this ozone layer out there to act as our shield. So only a small amount of ultraviolet energy reaches the Earth's surface. The molecules that absorb it out there give it back up. But when they give it back up, a lot of it is given right back out to space. So only a small amount is actually given in the direction of the Earth. Now, here's where the halogenated hydrocarbon comes in. It took a long time for it to happen because these molecules, these Freon molecules, took a long time before they finally migrated out far enough in the atmosphere to reach a point that they were subjected to this higher energy ultraviolet radiation. I'll get your question in just a second. This here is just a general formula. The Freon dichloro-difluoromethane is really called Freon 12. That's its chemical name. But there are other combinations of chlorine and fluorine, or fluorine and bromine, that are also freons. But Freon 12 is our most common one. When this halogenated hydrocarbon then reaches the outer atmosphere of the Earth, it is now subjected to this high energy ultraviolet radiation. And what happens is one of those chlorines, which was previously attached to a carbon, gets chopped off. The energy is enough to break the chemical bond, and the chlorine comes off now as a chlorine atom. Now, this is where then its problem could occur, where it could do its damage. This chlorine atom that we have now produced from the halogenated hydrocarbon reacts with an ozone to form this oxygen chlorine and goes back to just normal oxygen. We have thus destroyed one ozone molecule. One chlorine atom has destroyed one ozone molecule in the process. But this here, this ClO that was produced in this step, comes down here, reacts with an oxygen atom, which is necessary up in this process here to produce ozone, and produces another oxygen. So now we have not only destroyed an ozone in the process, we have now destroyed an oxygen which is needed to produce the ozone. So every chlorine atom now has destroyed or has the potential to destroy 2 ozone molecules. But worse than that, look what we ended up with at the second step. We ended up with the chlorine atom back, and that chlorine atom can go right back on up now and start the whole process over. And this one chlorine atom could go through this cycle time and time and time again. Every time it goes through the cycle, it destroys 2 ozone molecules. Either destroys the ozone molecule itself or destroys the potential of reproducing the ozone molecule that's needed to keep the level constant. If we add the equations together, then we end up with this right here as what we call the net equation, but we see then a chlorine atom reacts with an ozone and an oxygen atom to produce just regular oxygen, which doesn't protect us from ultraviolet energy, and gives us back the chlorine. So this just recycles back through, back through, back through for an infinite number of times. All right? Now, there was a question, or did I answer the question?
Yeah, I was just wondering what that symbol was. Is it a 2 or is it a D or an alpha?
The question was, what is this, I guess what you're at, this symbol above the line. That's called lambda. That's wavelength. That's a symbol for wavelength of energy. And all we're saying here is that it's involved with a wavelength of energy that we call ultraviolet energy. Okay, it's the ultraviolet energy that is involved in this process. So we'll put UV energy here. UV energy for ultraviolet. Now, as I said, in the lab we can duplicate this process. And we can show that in fact that a halogenated hydrocarbon under these conditions can possibly produce this decrease in ozone. But in the atmosphere, where we're talking at concentrations so low that we never work with them in the lab because of the time factor, we have to make some guesses. We're making some guesses that this in fact does occur in the outer atmosphere. And this is where the debate comes in. There are groups of chemists, very sound research chemists, that really debate whether halogenated hydrocarbons have had any effect on the ozone layer. They use the same data that the other group of chemists do, and they come to a different conclusion. There are those groups of chemists that claim, yes, in fact, this is occurring, and yes, in fact, that is why we see a decrease in the ozone layer around the Earth. Now, the question is, we're looking at a time period of a few years. When I say a few years, we've been looking at the ozone layer maybe for 10 years, certainly not much more than 15. So if we see a decrease in the ozone layer, is this because of man's effect with a halogenated hydrocarbon, or is this a natural cycle that would be occurring if man wasn't even on the Earth? We really don't know. You see, we have such a little time frame that we're looking at. What is happening to the sun's output could greatly be affecting what we see happening to the ozone layer. And if we don't have data that extend several thousand years, which we don't have, then we have to make some assumptions. And of course that's, as I say, where the debate came in. But this is what ultimately it came down to. Many of the groups, many of the countries throughout the world basically got together and said, what do we gain from the use of this halogenated hydrocarbon called Freon? Well, it's used in your home air conditioning, it's used in your home refrigerator and freezer, in your automobile air conditioner. It's used as a propellant for many things. The question was, how critical are these, or can we find something else to replace them? And the question was, if there was only 0.01% chance that the use of halogenated hydrocarbons did decrease the ozone layer. Let's just suppose that was the number. If that was the only chance there was that it decreased it, is it worth the risk of increasing possible skin cancer, cell mutations, etc. on Earth because of the advantage of being able to spray something out of a can? Or can we mechanically squirt it out with our finger instead and not use the halogenated hydrocarbons? This we refer to as risk analysis, and we do this all the time ourselves, but it's very important in science. Risk analysis. Yes, there is a risk, a possible risk associated with halogenated hydrocarbons. And if that is true, then how much risk are we willing to take? Well, the amount of risk we're willing to take is dependent upon, of course, the benefit that we can hope to gain from it. For instance, to give you an example, a person has cancer. One of the ways we can treat cancer is to do chemotherapy. Now, chemotherapy is injecting the body full of a lot of deadly poisonous chemicals. That's what we're really doing. There is an absolute risk involved in injecting a person with these toxic chemicals. The question there is a risk versus benefit. And the person with the cancer then says, yes, I'm willing to take this risk to go ahead and inject me full of these poisons in the hope that those poisons will more selectively destroy cancer cells than they will to affect my good cells. That's risk analysis. Well, the world, the major countries of the world, agreed that it wasn't worth the risk that we might be affecting the ozone by using these Freon compounds. They agreed, and they actually then, as a worldwide group, then agreed that by the year, I think it's 2000 or 2002, that these need to be phased out in use. We can't just stop immediately, because that would mean, what were you going to do with your air conditioner in your car? It's there and it's full of Freon, or your home refrigerator. But rather than continue to produce it and continue to increase the risk, we have decided that we would look for alternate chemicals to use as refrigerants and also for propellants, etc. Now, if you have an automobile today with a Freon charged air conditioner and you go to try to get it recharged, you're going to find some major problems. Okay? You're going to find very high cost, and you're going to find in many cases that Freon is no longer even available. It's a condition that we've now decreased the productivity and beginning to phase in other things. You'll still be able to use your air conditioner, but if it ever gets to the point that it does need recharging, you may not be able to do so. And then it will have to be modified to use one of the new chemicals that we have produced. So, risk analysis is very important. Anytime we're thinking about new chemical products, new processes, etc., we have to weigh how much advantage do we get from this thing, and if there is some risk, is that risk worth taking? In this case, most of the countries of the world agreed it really wasn't worth it, and we could find some other products. However, with that in mind, we also must remember that yes, today it might appear that those chemicals that we decide to use to replace halogenated hydrocarbons appear safe. But you see, when we started using hydrogenated hydrocarbons, everybody thought they were totally safe. They were chemically inert. They were tasteless, odorless, every good property we wanted. But it took some 15 to 20 years to realize that, in fact, there was a risk associated. So oftentimes we have to go back and re-evaluate our risk. Well, we'll go ahead and stop here for today. And then in our next lecture, we're going to take a look at using balanced chemical equations to solve problems, a technique called stoichiometry.